But once a neurodegeneration has happened, boy, you know, I would say 100% of neurologists will tell you none of those neurons are ever coming back. But wouldn't it be nice if it did come back? It's not just nice. It would mean something very different for humankind. Aging could be essentially cured if we could bring neurons back.
According to the World Health Organization, it is estimated that between 250,000 and 500,000 people suffer a spinal cord injury, or SCI, around the world. SCIs are typically the result of accidents, such as an automobile collision or unsafe operation of heavy machinery, that cause trauma to the spine, dislocating or fracturing vertebrae. While the use of medical devices, such as prosthetics and wheelchairs, can improve the quality of life for individuals living with SCI, there is no known cure, and these patients often live with the reality that their spine will never heal. But what if it were possible to regenerate the neurons lost during spinal cord injury? This is the question being posed by scientists studying adult neurogenesis, an emerging research focus that could have implications on therapies for everything from Alzheimer's disease and stroke to macular degeneration. In this episode of Vital Science, we're joined by Dr. Wise Young from the W.M. Keck Center for Collaborative Neuroscience at Rutgers University. He discusses his experience developing the first standardized rat SCI model used for therapy testing, the groundbreaking clinical trials he recently conducted in China, and why he thinks neurogenesis could be the key to a new age of treatment for SCI patients.
Welcome to Vital Science, Dr. Young. We are really honored to have you. So if you could, would you just tell us about yourself and your role at the W.M. Keck Center for Collaborative Neuroscience?
I came to Rutgers in 1997, and I built the center. And the center was built from ground up to be a collaborative center. It's designed for people to work together. And I think even more important, it's a place where we want to help the field actually work together. For a long time, spinal cord injury was one of the most competitive fields in science, and people weren't sharing with each other, people weren't talking with each other. And so in the early 1990s, in 1991, I decided to go ahead and spend a significant amount of my time, maybe the last half of my life, quite literally developing and implementing a rat spinal cord injury model that everybody could utilize, that could be reproduced over and over and over again, and really reduce the cost of spinal cord injury research, and also increase the reliability, the stability, and the reproducibility of the data, so that the data that we get now in 2022 is almost identical to the data that we got in our rats in the 1980s and 1990s. And we were funded by the NIH to do this. We called this the Multi-Center Animal Spinal Cord Injury Study. And I'm very proud of the fact that we got together the 8 leading spinal cord injury centers in the US to work together. And we called this the MASCUS, the Multi-Center Animal Spinal Cord Injury Study. And we spent essentially 5 years standardizing this model, so that every aspect of this model is completely defined. And we not only worked on the animal portion of it, but all the outcome measures. We established ways of assessing how the animals walked, how to do the neurophysiology, how to do the histology, et cetera, et cetera. So this was a very gratifying work. And I spent probably the better half of the last 25 years training close to 1,000 people every year how to do this model. And we were particularly lucky to have been working with Charles Rivers by using a particular rat that is called the RNU rat. The RNU rat is a rat that can receive cells from other animals without immune rejection of the cells. So this is a fantastic model for cell transplantation, and that's what we've been doing for the last, I don't know, 7 or 8 years. We've been using this particular, the RNU animals, to do our cell transplantation work. And of course, where all the stem cell research and so on forth comes from is from this animal.
Amazing. You know, so many have thought SCI to be an impossible therapeutic area for drug development. Can you tell us how you and your team were able to use this model to propel your research forward?
Yeah, well, I mean, I'm very grateful to my colleagues. The 8 leading spinal cord injury centers were our partners in all of this, and we trained many, many people in all this, not just the 8 centers, but we've trained many people all over the world. We just finished a series of animals from which we got all the preliminary, the preclinical studies that were done for our current clinical trial, and our mortality rate was less than 3%.
Wow.
Which is simply unheard of, and no animal who got treated at transplant died. So we had 0 mortality that could be attributed to the therapy itself. So it tells you a little something about the quality of the model, and also we have very, very consistent results. It really showed us how working together really made a model work.
Annually, only a small percentage of SCI cases worldwide are severe. This is largely due to the protective nature of the spinal cord itself. Many people don't realize that due to its elastic ligaments and discs, the spinal cord is actually extremely flexible. This flexibility is what protects the spinal cord, together with the meninges, which are layers of membranes that cover the brain and spinal cord. One of these layers, the arachnoid, holds the cerebrospinal fluid in which the spinal cord floats. Outside of this is an extremely resilient membrane called the dura mater, which translates to tough mother. This outer layer is so tough, it can be challenging to cut through, even with a scalpel. And so, when an injury is so serious that the spinal cord is cut or severely damaged, arachnoid, dura mater and all, the results can be devastating. Understanding the nuances of how the spine behaves after trauma has been critical to the clinical research Dr. Young has conducted over the last 40 years. Let's hear more from him on how treatment has evolved over this time.
I do want to dive into very early on in your work, when you've been navigating to find an effective rat model and the applications of that work through cell therapy specifically. If you could share a little bit more about your journey of finding the rat model, and once you did, what were the essential components for that work?
Well, I guess we discovered at least 2 drugs very early on that seemed to be beneficial when you give it to the animals very early on. One was a drug called methylprednisolone, and the other one was a drug called naloxone. And we took both of these to clinical trials, and it turned out methylprednisolone was better than naloxone. And methylprednisolone was used by, I think, most doctors throughout the 1980s and part of the 1990s. It's not enough just to do a clinical trial and show that it works. We showed it worked. It's just that people didn't really believe it. And so I guess it got not that much use. In the 1990s, I moved from acute spinal cord injury to chronic spinal cord injury. And that was because nobody in the whole world had any belief that you could do something after the injury has occurred, let's say a year or more later. And so I moved, and at the same time, I moved in 1997 to Rutgers, where I started working solely on chronic spinal cord injury. But I may be going back to acute spinal cord injury because they now don't have a therapy that people believe works for acute spinal cord injury. And And that's too bad. I just see too many people who are spinal injured, and they would write to me and they say, "Oh, what can we do?" And so I want to get the trials for chronic spinal cord injury completed. Then I'm going to return back to acute spinal cord injury.
And could you tell us more about the role of stem cells in these applications and how they help regenerate or heal the spinal cord?
Well, there are two things that we should remember about stem cells. That is, stem cells is what the body evolved to build the body. I mean, our stem cells, we start out with a whole bunch of with one stem cell. It was the egg. It becomes, and it makes the rest of the body, right? That's what stem cells really are. They can make many kinds of cells. And the nice thing about studying stem cells is we got to learn a lot about how the body makes itself. I mean, really, that part, I think, was the main reason why so many scientists wanted to study stem cells. And I went into a stem cell field that was not controversial. I went after umbilical cord blood. And the umbilical cord blood has almost everything that's necessary to build the whole body. So it's a nice thing to have that something like 30 million babies are born every year. And we can collect their umbilical cord blood and store it and use it to treat babies. And there's a lot of things in that umbilical cord blood that is beneficial. So a lot of these studies that I've done with the rats, with the RNU rats, was the transplantation of umbilical cord blood cells into these rats. And it had beneficial effects. And it was not just me. I mean, quite literally, hundreds of laboratories had reported beneficial effects.
While the rate of spinal cord injury in the United States is relatively low, it is much higher in China, where an estimated 60,000 people suffer SCI annually. Despite this discrepancy, very little SCI research has been conducted in China, where Dr. Young ultimately decided to pursue his clinical studies. Because it was such an emerging area of research, a significant amount of groundwork had to be laid in training surgeons and physicians on clinical trial procedures before the trials could begin. During this time, Dr. Young met the head of an Army hospital neurosurgery department who asserted that exercise played an essential role in SCI recovery. How much exercise? 6 hours a day, 6 days a week for 6 months. And so, in conjunction with administration of Dr. Young's cellular therapeutic, patients were also enrolled in the 666 walking program. Let's hear more about how exercise was a critical component of success in these trials.
That's incredible. And as I understand it, it's not as simple as just injecting the cells into the patients. Can you tell us a bit more about what the patient's journey to recovery looks like?
It's very interesting. I never expected some of these things. It's very, very interesting because people got used to the fact that they were walking. You forget the fact that you were a complete spinal cord injury and you couldn't move your legs or your arms or your body. And then, I mean, these people hadn't walked. Many of them had not walked for 10, 15, 20 years. And then after the 666 program, 75% of them walked. I mean, it's like they got used to it and they sort of expected this walking. And it's like they got...
Gives them hope.
Yeah, well, it's more than hope. They got it. They got...
Yeah, that's right.
They got the recovery in many ways that they wanted. And it's very, very, very interesting how, so by the way, I have a really wonderful staff at the Keck Center. And one of the people that I have there is, anyway, so she has a son who has a C12, which is the same kind of injury that Christopher Reeve has. And he was injured the same year as Christopher. And he is amazing man. Anyway, her son really taught me an incredible amount, that you should never, ever give up hope on somebody. who has a very high injury. I mean, there are two things that is very bad. One is having chronic spinal cord injury, that is, you've been injured for a long time, and then having a complete spinal cord injury, which means you have nothing below the injury site. Those are the most abandoned, hopeless people in the world. And Peter Morton really taught me a lot, not only about hope, but the fact that you can get better and recover, and that you should not give up. Anyway, so one of the nice things about doing spinal cord injury work is that we are, I get to meet a lot of families with spinal cord injury. And one of the very interesting things that worried me about our clinical trial was that, in order to do a clinical trial successfully and also in a credible way, you have to have a control group.
In Dr. Young's clinical trial in China, patients were randomized among the placebo and the control groups, and at the end of 1 year, given the option to receive the experimental treatment. Placebo-controlled trials are traditionally challenging to recruit for, as patients don't want to wait any longer than they have to receive treatment. So you can imagine what a curveball it was when Dr. Young had a patient request to be part of the control group. Why? Well, because the patient believed that in order for the regenerated neurons to truly work, his body would need to be primed through dedicated exercise in the 666 program prior to treatment. This reasoning spread like wildfire through the tight-knit SCI community, and patients readily signed up for the trial, knowing that whether they received the cell therapy concurrent with or after the 666 program, their bodies should be in a better position to benefit from the promised treatment. Later in our conversation, Dr. Young discussed other therapeutic areas where neurodegenerative therapy may be valuable.
I know it's taken a tremendous amount of work by yourself personally and together with other scientists and clinicians to bring your SCI studies to bear. Are there other disease areas that you think might benefit from this research?
I should say something first, because I think it'll maybe give you a better understanding. My mother's 95 years old, and she's lost a lot of her memory, and she has senility. And she's lost probably a lot of her neurons. And we're finding as we study more and more of the chronic spinal cord injury that a lot of the therapies that we've been working on actually will cause replacement of neurons in the spinal cord and the brain. Mm. And the two treatments that we've identified, one is lithium. It's the same drug that you use for manic depression. And part of this reason why I got into this thing was because in 2003, a professor at the University of Pittsburgh showed that if you give somebody who has manic depression lithium, and you give it to them for 6 weeks, and you do an MRI before and after 6 weeks, you find that their gray matter in the brain, the gray matter is where the neurons are, actually increases in volume by 15%, 15%. Wow. And furthermore, if you wait a year, that 15% is still there. So it's not just a swelling of the brain. It is actually the gray matter of the brain is growing. But the other treatment that seems to be effective for stimulating neurogenesis in the brain are these very microscopic particles that's in umbilical cord blood. And these are called exosomes. Exosomes is very, very hot right now because particularly umbilical cord blood exosomes, because umbilical cord blood exosomes is the primary method by which the placenta communicates with the baby and stimulates the baby to grow and to develop. But when we started studying exosomes in umbilical cord blood, we were stunned to find out how many exosomes there are in umbilical cord blood. Normally in your blood, in our peripheral blood, we have about 1 billion exosomes per milliliter. This is the dose that our body uses to send messages to all the cells in our body. Umbilical cord blood has 1 trillion exosomes per milliliter, 1,000 times more than peripheral blood of adults. And so, of course, what do? We developed a method of isolating these exosomes, and there's a very nice way of actually isolating these things in 20 minutes, and we can get 95% of them without damaging them and so forth. And then we put them onto cell cultures. And we were stunned to find out that these exosomes really stimulate cell cultures to grow like crazy. But even more interesting, it stimulates the cells to grow, but it does not make them produce tumors. And so it turns out that umbilical cord blood exosomes are about the safest source of exosomes you can get. You know, if you have exosomes in the body of an adult, lots of tumors and lots of bad cells in your body are making exosomes, and it's causing all these problems. And so what is very interesting is that at least exosomes do not cause tumors, and it seems to have some anti-infective effects. It also seems to have anti-inflammatory effects. So here it is. We've got a source of umbilical cord blood exosomes, and we're using them to grow cells.
So therapeutically speaking, what is the value of these exosomes?
Exosomes causes neurogenesis in the brain. What it does is it strongly stimulates the creation of new neurons in the brains of neonates that are born. And so it's really exciting that we now have two therapies, exosomes and lithium, that seem to stimulate new neurogenesis of neurons in animals. And we, of course, hope that this will be true for human. We're going to take this to clinical trials.
In the drug development journey, in the therapeutic development journey, specifically in cell therapy, when you're talking about concept to commercialization, it's not linear by any means. It's a very windy road with many challenges. So I'm curious to know, in what ways can collaborating with a contract research organization help programs like yours?
Well, without CROs, I think most of the clinical trials would not be done. And they have the discipline, the rigor, the ability to make sure that we follow all the rules. Most of us who do the clinical trials, I mean, if we don't follow all the rules, I mean, you can spend millions upon millions of dollars and have it wasted. So you really need a CRO to do the work for you. And so it's good, it's important. And this is how we can trust the clinical trials, because there are people who are looking and doing quality control, making sure that everything is done exactly the way it's said to be done.
Well, it is just incredible the amount of progress that you've made as both a researcher and an advocate in the SCI community over the last 40 plus years. Somehow, I don't think you'll be stopping here. What other initiatives are on the horizon?
Well, there's just a lot to do. You know, I have become very, very much interested in neurogenesis in the last year or two. Because, look, if there's one group of people who've been made more hopeless than any other group in the whole world, these are the people who have Alzheimer's disease and neurodegeneration. And it's really sad. There's a lot of work done on Alzheimer's disease to try to prevent the neurodegeneration from happening. But once the neurodegeneration has happened, boy, I would say 100% of neurologists will tell you none of those neurons are ever coming back. But wouldn't it be nice if it did come back? I mean, it's not just nice. It would mean something very different for humankind. I mean, aging could be essentially cured if we could bring neurons back. Because look, I mean, yeah, we can lose some muscles, we can lose some, but if you lose neurons, just nothing can bring those things back. I'm sorry, I mean, I probably won't have enough time in my life to take on another big project like this, but it is really, really exciting that I think we will actually get there, and it'll happen much faster than we possibly think. And the whole world is aging, the whole world.
Dr. Young, what do you hope your legacy will be?
Oh, well, I don't know. I don't think about legacy. I mean, I am very hopeful that the students who have worked with me and with my team really have taken to heart what we do and what we have been doing. I mean, they've seen quite literally thousands of scientists come in and learn how to do the spinal cord injury work. And they've seen how, we're slowly, one by one, changing the field. And I'm hoping that they see that this is what science is all about, to collaborate with others and to do this kind of stuff to help people. I'm very grateful to my undergraduate students. I have to say, they don't need to spend the many hours working in the lab, but they don't want to leave the lab because it's exciting. I mean, they're discovering things. They know what they're discovering will change the world. And I think from that point of view, they're not going to forget this. They're going to go on and get their MD, PhDs, and whatever, and they're going to help the world. I hope that's if anything, that should be, and I hope that would be my legacy.
Well, it sounds like you're influencing the next generation for sure. Well, Dr. Young, I just want to say thank you for pushing past these obstacles of people saying nothing can be done for spinal cord injuries and your pursuit of making a true impact to spinal cord research. Thanks so much for joining us on Vital Science.
Sure. It's my pleasure. And it's been fun. Thanks.
Dr. Wise Young is the founding director of the W.M. Keck Center for Collaborative Neuroscience at Rutgers University. Looking ahead to our next episode of Vital Science. In March, we'll talk with 13-year-old Evie and her mother Lindsay about hypophosphatasia, a rare metabolic bone disease, and how a treatment with a novel enzyme replacement therapy has changed Evie's life. Until then, thanks for listening.